Good morning. Let us continue our discussion for recurrence relations, second order. We were discussing non-homogeneous second order recurrence relations, and for non-homogeneous, these were the four cases. Fn is a polynomial of degree q, and 1 is not a root. This was one case. Second case is 1 is a root. This was the solution for that. The third case is Fn is of the form alpha b to the power of n, and b is not a root of the characteristic equation. Then the form for particular solution was a0 b to the power of n. The fourth case was Fn is in the form of alpha b to the power of n, and the solution will be of the form a0 n to the power of m b to the power of n. M is the multiplicity of the characteristics equation, and b is the root. Okay, so these were the cases we are discussing about. Case 3, function fn is of the form alpha b to the power of n. Here b is not a root of the characteristic equation. Then the particular solution will be of the form a0 b to the power of n. The next case is a function fn is of the form alpha b to the power of n. Here b is a root of multiplicity m. The solution for that was a0 n to the power of m b to the power of n. And here we'll take directly one example and try to understand. First of all, this is a non-homogeneous recurrence relation, as on the right hand side you don't find 0. But here n is greater than or equal to 0, that has to be converted to n is greater than or equal to 2 for second order. The general form of this is Cn an plus Cn minus 1 an minus 1 plus Cn minus 2 an minus 2 equal to Fn. Right hand side is Fn is, here a function Fn is 3 to the power of n. So for this the solution an equal to an homogeneous plus an particular. So first take the LHS, solve the LHS, an homogeneous. So that will be an plus 2 plus 3an minus 1 plus 2an equal to 0, as n is greater than or equal to 0. Now here we are going to substitute n with n minus 2 as we want to make it second order. So this becomes an minus 2 plus 2 plus 3an minus 2 plus 1 plus 2an minus 2. So that comes to be an plus 3an minus 1 plus 2an minus 2. Now here C1, value of C1 is 1, value of C2 is 3, and value of C3 is Cn minus 1 is 3 and Cn minus 2 is 2. Cn minus 2 is 2. What is the general solution? The general solution is Ck to the power of n. That is, wherever you find an, substitute that with Ck to the power of n. So this an will be substituted with Ck to the power of n. This an minus 1 will be substituted with Ck to the power of n minus 1. This an minus 2 will be substituted with Ck to the power of n minus 2. This is our form: Ck to the power of n plus 3Ck to the power of n minus 1 plus 2Ck to the power of n minus 2. Now we are going to substitute n with 2. So it will be Ck square plus 3Ck plus 2C. So we are ignoring C, so that becomes k square plus 3k plus 2. Simplifying this in this fashion, we will be getting the value of two roots, k1 as minus 2 and k2 as minus 1. The roots are real and distinct. When the roots are real and distinct, this is case 1. The two roots k1 and k2 are real and distinct. Then the solution is an is equal to ak1 to the power of n plus bk2 to the power of n. So ak1 to the power of n plus bk2 to the power of n. So here the value of k1 is minus 2 and the value of k2 is minus 1. Substitute that. So we will be getting it as a minus 2 to the power of n plus b minus 1 to the power of n. Here a and b are the arbitrary constants. Now what remains? What remains is the RHS function fn. What is the function fn? Let us look at the RHS. So what is given on the RHS? 3 to the power of n. On the RHS 3 to the power of n is given. So RHS is of what form? This 3 to the power of n is of what form? It will be of this form, alpha b to the power of n, and b is not a root. So the solution will be a0 b to the power of n. The solution will be a0 b to the power of n. Here we are written a0 b to the power of n. So here in this case b is 3 and alpha is 1. So substitute b with 3, so you get a0 3 to the power of n. So now we get an is equal to a0 3 to the power of n. This we are going to substitute in our relation. What is our relation? An plus 2 plus 3an minus 1 plus 2an is equal to 3 to the power of n. So wherever I find an, I will be substituting that an with a0 3 to the power of n, or rather a0 bn. So here as it is an plus 2, this will become a0 bn plus 2. As it is an plus 1, this becomes a0 bn plus 1. As it is an, it becomes bn. So our new equation after substituting a0 3n is equal to a0 3n plus 2 plus 3a0 3n plus 1 plus 2a0 3n 3 to the power of n is equal to 3 to the power of n. That after simplification what we will be getting is a0 equal to 1 by 20. You can see it is simplification is easier, right? So I have taken out 3n common. Now what remains is on the right side 3n is there, on the left side 3n is there. They will be cancelling. What remains is the whatever was there in the bracket. So that is a0 3 square plus 3a0 3 1 3 to the power of 1 plus 2a0. That becomes 9a0 plus 9a0 plus 2a0, that will be 20a0. So a0 will be equal to 1 by 20. This 1 by 20 will be putting in the equation. Which equation? A and p equal to a0 3 to the power of n. So a0 is 1 by 20. So 1 by 20 3 to the power of n. Now what is our solution? Our solution is for homogeneous is this: a into minus 2 to the power of n plus b into minus 1 to the power of n, and particular is 1 by 20 plus 3 to the power of n. So both of them we are adding together. So we will be getting this: a into minus 2 to the power of n plus b into minus 1 to the power of n plus 1 by 2 into 3 to the power of n. Here we need to find out a and b, and what is given in the question? In the question a0 is 0, a1 is 1 for n equal to 0 and n equal to 1. So for n equal to 0 we will be substituting the value of n to be 0, okay, and that becomes, here this n becomes 0, this n becomes 0, this n becomes 0. So this is the first case wherein you will be getting this 0 is equal to a plus b plus 1 by 20. The second case is a1 equal to 1. Wherever n is there, you will be substituting that with 1. So n is 1, here n is 1, here n is 1. So after simplification you will be getting this 1 equal to minus 2a minus b plus 1 by 20 into 3. So using these two, after simplification what we get is a is equal to minus 4 by 5 and b is equal to 3 by 4. So we will be substituting the values of a and b in our equation, and that becomes our solution. So wherever a is there, minus 4 by 5. B is there, 3 by 4. We will take one more example. So we can see that this is a non-homogeneous recurrence relation, as on the right hand side the function is 5 into minus 2 to the power of n instead of 0. So for this, what is the general solution? First find the an homogeneous, then find the an particular. So an homogeneous is left hand side. Take the left hand side, an plus 4an minus 1 plus 4an minus 2 equal to 0. Use the same general form. Here we get the value of Cn as 1, Cn minus 1 as 4 and Cn minus 2 as 4. So substituting an with ckn in the above, what we get is ck to the power of n plus 4ckn minus 1 plus 4ck to the power of n minus 2 equal to 0. Simplifying this, we will be getting the roots as minus 2 and minus 2, which are real and equal. When the roots are real and equal, that becomes our case 2. What is our case 2? K1 and K2 are the roots. These are real and equal. Then the solution will be of the form a plus bn multiplied by k to the power of n. So a plus bn multiplied by k to the power of n. So a plus bn multiplied by minus 2 to the power of n, because the value of k is minus 2. K, what is k? K is the root. Now comes the RHS part. RHS part is 5 into minus 2 to the power of n. So this is of the form alpha into b to the power of n. Alpha into b to the power of n. And what is the value of b? The value of b is minus 2. And what is the value of roots? The value of roots is also minus 2. So it comes this form, okay, where the form is alpha into b to the power of n. B is a root of multiplicity m. So the solution will be of this form: a0 n to the power of m, b to the power of n. The solution will be of this form: a0 n to the power of m, b to the power of n. The value of n will be 2. The value of b is minus 2. So substituting that, you will be getting a0 n square multiplied by minus 2 to the power of n. So an will be getting as a0 n square minus 2 to the power of n. Now we will be substituting this in the relation. What is our relation? An plus 4an minus 1 plus 4an minus 2 equal to 5 into minus 2 to the power of n. So wherever I get an, I will be substituting that with a0 n square multiplied by minus 2 to the power of n. So that becomes this: a0 n square minus 2 to the power of n plus 4a0 n minus 1 whole square into minus 2 to the power of n minus 1 plus 4a0 n minus 2 whole square into minus 2 to the power of n minus 2 is equal to 5 into minus 2 to the power of n. So we are dividing the entire LHS and RHS by minus 2 to the power of n minus 2. So when I do that, I will be getting, after simplification, this values of a0 coming to be 5 by 2. This I will be substituting here in my particular solution. I will be getting 5 by 2 n square minus 2 to the power of n. So now my complete solution will be an homogeneous plus an particular. So an homogeneous plus an particular. An homogeneous plus an particular. Once I add, I get the solution. Thank you.